Hi everybody, my name is Navid and today I'm going to present our paper named Individualizing Head-Related Transfer Functions for Binaural Acoustic Applications, which has been done in collaboration with Dr. Anil Mohandas and Dr. Ron Zheng. What is Head-Related Transfer Function or HRTF? Consider two sounds being played from directions 1 and 2. Humans can perceive the direction of these two incoming sounds and differentiate between them. This is because the sound goes through different paths before reaching each ear, as you see for sound source number 1. More to that, the path that sound source 2 goes through is different from sound number 1. Both sounds go through the filtering effects of the ear, head, and torso before reaching ears. This filter is called Head-Related Transfer Function, or HRTF, and is defined separately for each ear. Knowing this filter enables a lot of applications, but it's not a trivial task. Why? Because as I mentioned, HRTF is related to physical attributes of the body. HRTF of two persons with different size of head, different shape of ears, and overall different physical properties is not the same. And this makes HRTF a subject-dependent filter. As an example, here is a 3D scan of ears of 6 different subjects, and you can see the difference in the shape and size. Moreover, as you saw here, for sounds in position 1 and 2, HRTF is direction dependent. So if I want to use the HRTF of a subject for a specific application, I need to know it for all the desired directions in space. HRTF is gaining more interest as more people are wearing wireless earbuds during their daily routines. HRTF's main application is in 3D sound spatialization. For example, as a navigator in museums or airports, which gives you hints for arriving at your destination while you follow the direction of the sound played through earbuds. Or in AR and VR games, it's used to create a sense of immersion for their interaction with the environment by perceiving the direction of the played sound. How does it work? By convolving a mono sound with left and right ear HRTFs separately and playing the corresponding sound through left and right earpieces, which gives you a sense of externalization as you would sense a real person is actually talking to you from that specific direction. Moreover, by wearing earbuds, your awareness of your surrounding diminishes. Using HRTF, we can do binaural detection and localization of sound events using only two microphones and alert users. However, current products in the market use a general or non-individualized model, which leads to perception and localization errors. Why do they use general HRTFs? Because there is not yet a practical, accessible method for HRTF estimation. One of the main methods for HRTF personalization is doing binaural acoustic measurements in an anechoic room for all the desired spatial directions. Multiple speakers are installed on an arc. You stand in the center of the arc. The sound is played from each speaker and the response is recorded with in-ear microphones. Then the arc rotates around you and repeats the process to cover all directions. This process needs a special room and equipment, which is not accessible to everybody. Some have tried to regress the HRTF of users by measuring anthropometric data of the user or simulating the acoustic propagation around the user's head. Both approaches need 3D scanning of head and ears, which is still in need of a special equipment. There have also been some efforts on estimating HRTF with perceptual feedback. User listens to 3D sounds through headphones, and based on the user's feedback on the perceived direction of the played sound, the estimate of HRTF is corrected, which takes time and is not always user-friendly. So the main idea behind our work was how can we make this process easier? First of all, it should be accessible to everybody. So our proposed solution uses commercial off-the-shelf devices. Using their smartphone and in-ear microphones, people can measure their own HRTF in the comfort of their homes. Second, it should be fast. So measuring all the desired directions is not practical. They only need to measure some sparse directions. But how do we estimate their HRTF for other not measured directions? With the help of the second main component of our algorithm, which is a neural network model, which can estimate the HRTF of the user in all desired arbitrary directions in 3D space. The model is pre-trained on public HRTF datasets to learn the underlying sparse structure of HRTFs, which shows a high correlation among neighboring angles. With only 5 minutes of data collection, our model can estimate your HRTF. How do we collect data from any user? To collect data from users, we ask them to hold a mobile phone in hand and stretch their arms as far as possible. Then move the phone around in all directions, pause at arbitrary positions, and play a reference sound with the phone. The sound is recorded by two in-ear microphones. Then, by having the direction of the sound and the recorded signal, we can calculate the HRTF of the user at that specific direction. The direction of the sound is estimated using the embedded IMU sensor of the phone, which results in all calculated directions to be in the phone's frame, which is not desired. In order to calculate the directions with respect to the desired frame for HRTF, we ask the user to do measurements using both hands. Then, with the help of simple geometry and some characteristics of HRTFs, the unknown parameters required for our transformation are estimated. Now we can calculate the desired HRTF function at all visited positions during measurement, which are shown with red dots. Then, with the calculated HRTF at these positions, our neural network model can estimate the HRTF in all other directions. We have done some experiments to show the performance of our proposed algorithm. First, we show the fidelity of our algorithm for estimating HRTF of users. Our proposed neural network model is used to estimate the HRTF of 11 different subjects from the ITA dataset. In figure A, you can see the error in the red line, which is lower compared to a non-individualized model shown in black line. We show the time efficiency of our model. In figure B, you can see the effect of the number of sparse locations used for HRTF estimation. As you can see, with as low as 70 measured locations from a user, the model can estimate their HRTF with a lower error compared to the non-individualized model. Moreover, in our proposed measurement procedure, measuring points in the back of the head is hard. In both figures A and B, you can see the effect of collecting data from the users only from the frontal hemisphere, shown with a blue line, which leads to a slightly lower performance, but it's still a big improvement over the non-individualized or general model. Next, we do binaural localization test to estimate the direction of an incoming sound with only two in-ear microphones worn by a user. We compare the localization performance in 3 cases. The blue line is subject-independent or general model, which is trained using HRTF of all subjects in the ITA dataset, which is an average model of all subjects. Subject-dependent model is trained on ground truth HRTF of the respective subject. Subject-adapted model is trained on the HRTF estimated using our proposed algorithm. Compared to using a general HRTF, we can see improvements in localization error when HRTF is estimated using our proposed algorithm, with an average error of fewer than 10 degrees. To sum up, we proposed a lightweight individualization algorithm based on collecting sparse data from the user. Our proposed data collection procedure can be done at home using commercial off-the-shelf devices in less than 5 minutes. And using our proposed neural network model, the HRTF of the user can be estimated at all directions. For future works, we will further develop faster and more robust data collection procedure. Currently, it's hard to estimate points in the back of the head, which lowers the accuracy of the estimated HRTF. Also, by removing some of the constraints of the measurement procedure, like allowing the user to move the phone continuously, the process can be made a little easier. Thank you all for listening.